If we want to experience a productive and fruitful round of revision for H2 Math, it is actually very critical for us to first recognize whether the topic that we are studying is a theory-centric topic or whether it is a practice-centric topic. If it is a theory-centric topic, for example, topics like functions, for example, topics like vectors, they are very theory-centric, which means that you are supposed to revise the theories and the concepts first before you allow yourself to start practicing. Because if you were to just start by practicing, then the practice is going to be very unproductive, it's going to be very inefficient. So for those few theory-centric topics, we have been focusing on the theories for the last few weeks, and I hear a lot of good feedback from you guys because as you are doing your revision package, you feel so much more enlightened because we have cleared a lot of doubts in terms of the theories for those topics. But when it comes to a practice-centric topic, it is actually possible to get very much warm up through a few rounds of practice without even studying or recapping that much on the theories. But of course, if there were to be some theories, if you're unsure, please take a look at our Achevas TV and please take a look at your school's notes. They are going to be helpful, but practice by itself is probably going to get us warm up enough. And integration technique is a very practice-centric topic, and that is what we are going to try to do in the next 2 hours. We're going to get ourselves warm up and revise integration technique by going through some questions together. So I want you to do in these few integration techniques question together with me, and I want to adopt a strategy. So I want you to try to do this together with me also. Our strategy will be this. By default, if I'm planning to do a round of integration, I'm going to try to see whether I can work on standard results to integrate, based on standard results to integrate, or try to integrate using fx, f prime x, which means that when I look at an integral, I'm going to try to ask myself whether I can do some manipulations, for example, manipulations like partial fractions, like long division, completing square. I can also apply trigonometric identity so that I can get the condition right before I can then apply all the integration formulas that we have learned, the standard formulas that we have learned or memorized, and also applying fx, f prime x. And if this default strategy fails, then we are going to try to apply integration by parts. Actually, this is where a lot of students make mistake, which is to prioritize integration by parts when actually it is possible for you to be integrating it using standard results or using fx, f prime x. We are going to see one such case later, and let's try to get the idea of why integration by parts is actually a secondary strategy, a backup strategy. And we have one more technique, which is integration by substitution. For substitution, we will always be triggered by the question. So unless the question tells me so, or else I will not introduce integration by substitution. So let's take a look at the first question. We are going to be just working on integration technique for the next 2 hours. So try this together with me. So with your pen ready, let's start. Question number 1 from JJC. In 1a, we are supposed to integrate sine 2 theta, cosine 3 theta, d theta. Let's refer to what we have in our formula sheet. So on our formula sheet, if we were to look at the section on trigonometric identities, what we are going to try do is to spot an identity that is as similar to this expression as possible. And to me, that would definitely be here, sine A, cosine B. I'm going to focus on the first identity that we have there. And if I were to just recode that identity, rewriting A to be 2 theta, B to be 3 theta, this is what I will have. We will have a sine, rewriting A as 2 theta plus rewriting B as 3 theta. So this, I will write it as 3 theta. This is going to be equal to sine 2 theta cosine 3 theta plus cosine 2 theta sine 3 theta. There's also another version, which is going to be sine 2 theta minus 3 theta, and this will be sine 2 theta cosine 3 theta minus cosine 2 theta, then sine 3 theta. I will call this equation A, and I'll call this equation B. And the aim is to try to re-express this by trying to add A and B together. So if I were to add A and B together, on the left-hand side, this we will have a sine 5 theta, and this we will have a sine minus theta. And on the right hand side, when I add them together, this will be 2 sine 2 theta cosine 3 theta, and this will disappear. So now I can try to make this a subject, and that will be sine 2 theta cosine 3 theta. 2, let me divide it across, it becomes half. So half of sine 5 theta. Sine minus theta is the same as minus sine theta. So let me write it as minus sine theta. And this gives me an alternative way to express this. And if I can just replace this by my result here, it is going to be half then sine 5 theta minus sine theta d theta. And individually, they are now easy for us to integrate. There's another way that I can try to re-express this, and still making use of the first identity, but re-expressing what we have here into, let's say, cosine 3 theta, sine 2 theta instead. Okay, just switching this. So if I were to go for this version, rewriting using the very first one, and the reason is because now I am seeing this cosine A, sine B. Okay, the second term that is on the right hand side. That's synchronized to this, which means that A is going to be replaced by 3 theta and B is going to be replaced by 2 theta. So if I were to go for this perspective, then we will have a sine 3 theta plus 2 theta. This is sine 3 theta cosine 2 theta plus cosine 3 theta sine 2 theta. Okay, and this is what I'm going to try keep if I were to go for the same strategy. The other version will be sine 3 theta minus 2 theta. This is going to be sine 3 theta cosine 2 theta minus cosine 3 theta sine 2 theta. Calling this equation A, calling this equation B. How can I combine A and B together so I can be keeping this? And that will be taking this time equation A minus away equation B. And on the left hand side here, we will have a sine 5 theta minus away. This is going to be sine theta. It's equal to this minus this disappear. This minus minus become plus. So we have a 2 cosine 3 theta sine 2 theta on the right hand side. Now making this the subject, we will have cosine 3 theta, then sine 2 theta is equal to half of sine 5 theta minus sine theta. So replacing this by half sine 5 theta minus sine theta, we're actually getting back exactly the same thing. And now let's integrate this half. I'm going to just factorize it out. And for this, when I integrate sine 5 theta, it is going to be minus 1 over 5 cosine 5 theta. And when I integrate sine theta, it is going to be minus cosine theta. So minus minus become plus. So we have a plus cosine theta. And let's not forget about the plus c. So it will be half times this, gives me a half cosine theta. Half times this gives me a minus 1 over 10 cosine 5 theta, then plus c. In 1b, we are supposed to do substitution. So this is triggered by the question. So to do the substitution for 1b, we are given theta to be equal to square root of x. And we are supposed to integrate from square root of pi over 2 all the way until square root of pi of theta to the power of 3 cosine theta square d theta. So we are going to be replacing all the theta by x. So for what I have here, I'm going to do a differentiation with respect to x. This is like x to the power of half. We are going to be replacing all the theta. So d theta dx, this is equal to half x to the power of minus half, which is equal to 1 over 2 square root of x. And we need to replace this theta and this theta also, which means that when theta is equal to the lower limit here, square root of pi over 2, x is going to be equal to theta square. So square root of x is going to be equal to theta, which is square root of pi over 2. X is theta square, so this is going to be equal to pi over 2. So if I can rewrite this, this will become pi over 2. Similarly, when theta is equal to square root of pi, square root of x is equal to square root of pi. So x is equal to theta squared. This is equal to pi. So here we have a pi. And we are going to do all the replacement. So theta to the power of 3 is going to be this to the power of 3. So we have a x to the power of theta to the power of half to the power of 3. This is to the power of 3 over 2. And we have a cosine theta square. Theta square is x. So here we have a cosine x. D theta is going to be replaced by 1 over 2 x to the power of half. Then here we have a dx. So x to the power of half and this can be cancelled. We are going to be left with x to the power of 1. So what we have now is going to be equal to 1 over 2. I'm going to take it out of the integration notation. So here I have a pi over 2. This is going to be equal to pi. And this is going to be x. Then we have a cosine x dx. And in order for us to integrate this, very quickly, we got to think of whether we should do any manipulations so that we can achieve some kind of standard results or fx, f prime x in order for us to integrate this. And sadly, we don't have. And that is when we are going to make use of our backup strategy, which is to do integration by parts. And I believe we can apply the idea of LIATE. So for what we are seeing here, we are seeing an algebra, A, and we are seeing a cosine, so this is T. So LIATE, A comes before T. I'm going to let U be equal to X, and I'm going to let dV dx be equal to cosine X. So from here, I will be able to get du dx, this is 1. And V integrating this is just going to be sine X. So now I can re-express this into uv. So we have a x sine x from pi over 2 to pi. Minus away, integrating from pi over 2 to pi of v du dx, which is just going to be sine x dx. So we are going to try integrate this further. For this, we can evaluate the integral. So if I were to put half in, we have a, if we were to put pi in, so we have a pi sine pi. Sine pi is 0. So we are going to have a 0. Minus away, putting pi over 2 in, we have a x is pi over 2 and sine pi over 2 is 1. So minus away, this will be pi over 2. Minus integration of sine x. This is a standard result. So integrating sine x, we are going to get a minus cosine x. So this is minus cosine x from pi over 2 to pi. So we have a half. And now for this is equal to minus pi over 2 minus away. If I were to substitute in pi, cosine pi is minus 1. So minus 1 is going to be positive 1. Then minus cosine, minus of cosine pi over 2. Cosine pi over 2 is 0. So here I have a 0. So my final answer here is going to be equal to a minus half. Then after that, minus pi over 4. This is our question number 1. Let's move on. I hope you are already starting to get more warm up to integration. If not, it is fine. Let's continue to press on to integrate, because the more we integrate, you'll realize the more warm up we are. Then probably for some of you guys, after our 2-hour sessions here on integration technique, you're probably going to be almost ready for exam. Maybe you can just try a few more integration questions yourself, then you probably will be ready. And please take note of this recorded video that we are doing right now, because it is actually very, very useful that you guys come back and revisit this again. Almost every time when you need to warm up to integration, just come back. You know, redo these few questions together with me. I believe it is going to be a good and productive round of revision for you. So let's take a look at question number 2. Question number 2 from CJC A. We have to integrate 2 minus x over 4 plus x squared dx. So I got to ask myself, should I do some manipulation first? Do I need to do some manipulations first before I can apply any of the standard results or fx, f prime x? I think that is potentially possible. So let's see what we can manipulate to this in order for us to use some standard results or use some fx, f prime x, since that is our default strategy. So we should try as much as possible to explore from that direction first. And I think a good way is to break up this integral into two parts. So the first part is going to be 2 over 4 plus x squared. And I think 2, which is a constant, maybe I should just take it out of the integral. So we have a 2 of 1 over 4 plus x squared. And I know I can integrate this because this will become the tangent inverse. And for the other part, it is going to be minus of integration of x over 4 plus x squared. And this is fine also, right? Because if I were to let fx be the denominator, which is 4 plus x squared, then f prime x is going to be 2x, which I can very easily find in the numerator here by just introducing a constant into the integral. So for this, I'm going to rewrite it as 1 over 2 squared plus x squared. I have the standard results. I have the standard formula in order for me to integrate this. In fact, it is found in my formula sheet. Then minus away this, I'm going to introduce half so that I can have a 2x. Then we have a 1 over fx, which is going to be this dx. This is going to be equal to 2. By applying the formula, it is going to be equal to 1 over 2 tangent inverse of x over 2 minus away half. This is going to be ln of modulus of 4 plus x squared plus c. So let me just do one final calculation. So this is going to be 1. So we have a tangent inverse of x over 2 minus away half of ln modulus of 4 plus x squared. And I think it is a good habit for us to recognize how we are going to manipulate the modulus notation. How are we going to manage the modulus notation? Because if I were to mod something that is always positive, then it doesn't really matter whether I should have a modulus or not, because it is going to remain exactly the same, which is happening here. 4 plus x squared is an always positive expression. So I think I'm going to just replace this by a curved bracket instead of retaining the modulus. The reason why this is a good habit is because Cambridge does this all the time. Whenever Cambridge sees a positive expression, if it were to be modulus, Cambridge will remove that modulus and replace it by a normal curved bracket. So as we progress towards our A-level, we just want to get accustomed to this means of expression that is by Cambridge, so that we won't be we won't be allowing ourselves to be subjected to any bit of shock in the exam. So A, I guess this is a pretty okay question, 3 marks. Next, we are supposed to use a substitution, B. Let's try it. So B, we are supposed to substitute using this equation here. And we are supposed to be integrating from 0 to 1. We are supposed to be integrating from 0 to 1 of 1 over square root of 1 plus x squared. Okay, we are supposed to integrate this. So we are going to be replacing all the x by y. So I need to be replacing this dx. So I guess we have to find dx dy, which is secant square y. 0, 1, they are x values. So I want to also replace them by the corresponding y values. So when x is equal to 0, that means tangent y is equal to 0. This tells me that y is equal to 0. So 0 is going to be replaced by 0. And when x is equal to 1, tangent y is equal to 1. This is obvious. Y is equal to pi over 4. So here is a pi over 4. Then 1 over square root of 1 plus x squared. X is tangent y. So we have a tangent square y. dx is going to be replaced by secant square y dy. And we're going to make use of trigonometric identity. It is our default strategy to manipulate this. Hopefully we can then derive at a form that we can integrate using standard results or integrate using fx f prime x. And this, let us continue. pi over 4. 1 over square root of 1 plus tangent square y. Trigonometric identity tells us that this is going to be equal to secant square y. And we have a secant square y here, dy. So this is integrating from 0 to pi over 4 of 1 over secant y, secant square y, dy. Cancelling them, we are going to be left with a secant y. So 0 to pi over 4 secant y dy. And secant, and to integrate secant, we actually have a formula that is inside our formula sheet, the MF26. So I'm going to just use the formula. This is going to be ln of modulus of secant y plus tangent y. This is from our formula sheet. And we are going to apply the definite integral with the lower limit and upper limit. So this, we will have a ln of secant pi over 4. Secant pi over 4 is a special angle. Pi over 4 is a special angle, so it is going to give us a square root of 2. Plus tangent pi over 4 is 1. So we have a 1. Then minus away ln of secant 0. 1 over cosine 0 is 1. Then plus tangent 0 is 0. And we have a ln 1, which is 0. So my final answer is going to be ln, this is a always positive number. So I will just use the normal curve bracket. Oh yeah, okay, we have already gotten the answer. I guess this is still pretty manageable. Let's take a look at C. C is a tiny little bit tricky according to what we have mentioned just now. This is our strategy and I want you guys to try to stick to the strategy together with me. The default strategy is to manipulate to get standard results or to try apply fx, f prime x. Only if this fails, then we will apply our backup strategy, which is integration by parts. And I believe that there will be significant number of students during the exam that will apply integration by parts to see first part. The first part says that we are supposed to integrate x squared e to the power of x to the power of 3 dx. And I think probably this is just going to be a 1 or maximum 2 marks question. Most likely it's going to be just 1 mark. So if you are applying integration by parts, it is going to become unnecessarily tedious. So what is our default? Our default is manipulate to standard results or fx, f prime x. And I can apply fx, f prime x here, right? Because if I were to let fx be equal to x to the power of 3, then f prime x is simply 3x squared, and I can very easily get it here. This is 1 over 3, and we have a 3x squared. This is my f prime x, e to the power of x to the power of 3 dx. So integrating this, it is just simply e to the power of x to the power of 3 plus c. So please don't be tricked, or rather please don't allow yourself to be tricked by yourself by thinking that integration by parts is good. It is supposed to be prioritized before standard results and fx, f prime x. But why is it that integration by parts shouldn't be prioritized? Of course, if you have experience in that particular integral and you realize that integration by parts is going to work, go ahead and try it, okay? But if you're unsure, you should be exploring standard results or fx, f prime x first, because integration by parts is not trying to add a full stop to your integration process. It is a comma to your integration process. Integration by parts is a process of manipulation. It's not a process to finish up, to conclude an integration. That is why even after you have carried out an integration by parts, you are supposed to continue integrating some more. But if you can find a way to manipulate it to use standard results or fx, f prime x, you can conclude the integration. That is the reason why we should try standard results or fx, f prime x first, because they are helping us to finish up a process of integration. So if you were to look at the second part, it says hence we are supposed to integrate x to the power of 5, e to the power of x to the power of 3 dx. And this is the one that we are going to be doing integration by parts. Why? Because number one, the question says hence, so it makes it very obvious that we are supposed to be making use of the previous part. And secondly, if you were to look at this, And if you to give it a try, you will realize that no matter how much you manipulate this, it is not really possible for you to apply any of the standard results or any of the FX prime x. That is when we are going to go for our backup strategy, which is integration by parts. And for integration by parts, we do need some trial and error. It really depends on the question. So for this, although the question didn't really say, but the hint that is given to me is, hence I'm supposed to make use of this. So I think I'm going to break this x to the power of 5 up into x to the power of 3 multiplied by x to the power of 2. So if it is x to the power of 3 multiplied by x to the power of 2, let's see whether it is going to work. Because if it doesn't work, it is fine. I'm going to just find other ways to apply integration by parts by regrouping them into some other expressions. So the reason why I am trying out this first is because I have the integral to this, which means that for this particular part of the question, for this particular kind of integration by parts, we are not using LIATE. So please don't overly rely on LIATE. There are questions that doesn't require us to do your LIATE. There are questions that require us to use our own judgment to assign U, to assign dV dx. And usually when it is questions that are like this, you will focus on the dV dx first. Obviously, the reason is because it is usually harder to integrate than to differentiate. So my focus will be dV dx and asking myself, of these two, which one is easier for me to integrate? And of course, I'm going to make use of the previous result to try, because if I were to let dV dx be equal to x to the power of 2, then e to the power of x cubed, then v is already integrated here. V is going to be 1 over 3 e to the power of x cubed. So u is going to be this x to the power of 3, which means that du dx is 3x squared. Let's try to re-express this, and hopefully we will be able to finish up our integration. By parts is adding a comma to our statement, not a full stop. So adding this comma, we are going to expect ourselves to integrate some more. It is going to be uv. So we have a 1 over 3 x to the power of 3 e to the power of x to the power of 3 minus v du dx. So this times this, 3 and 1 over 3 can be cancelled. We are going to be left with x squared e to the power of x to the power of 3 dx. And I guess this question has in a way been set up because this is exactly this. So I'm going to just make use of the same result again. And my final answer here is 1 over 3 x to the power of 3 e to the power of x to the power of 3 minus 1 over 3 e to the power of x to the power of 3 plus c. Let's try question number 3 from YJC. For question number 3a part 1, we are supposed to integrate cosine 3x, cosine x. And what we're going to do again is to make use of what we have in our formula sheet. So in our formula sheet, going to the section on trigonometric identities, we want to try to look for an identities that can give me an expression that looks as similar to this as possible. And I would say that will be the second identity over here, cosine A, cosine B. And what I'm going to do is I'm going to replace A by 3x and I'm going to replace B by x. Quoting the second row's identity, that will be cosine, replacing A by 3x. So it will be 3x plus B, replacing it by x. It will be cosine 3x plus x. This is equal to cosine 3x cosine x minus sine 3x sine x. Then quoting the other version of the identities that is in the second row, it is going to be 3x minus x. And this is going to be cosine 3x cosine x plus sine 3x sine x. Calling this equation A, calling this equation B. How can I combine the two equations together? So I'm going to be left with a cosine 3x cosine x, and that I guess you'll be adding the two equations together. So taking equation A plus equation B, on the left hand side we will have a cosine 4x plus, this is going to be cosine 2x. And on the right hand side, this and this gives me a 2 cosine 3x cosine x. This plus this they will disappear. So making cosine 3x, cosine x the subject, cosine 3x, cosine x is going to be equal to half of cosine 4x plus cosine 2x. And this is what I'm going to be making use of to re-express this, which will now be a half. Then cosine 4x plus cosine 2x dx. Factorizing out the half, we will just be integrating cosine 4x, which will be 1 over 4 sine 4x. Integrating this, it is going to be equal to 1 over 2 sine 2x. Let's not forget about the plus c, so my answer is going to be equal to 1 over 8 sine 4x plus 1 over 4 sine 2x, then plus c. I'm going to leave this here for our reference. So for part 2, we are supposed to integrate from 0 to pi over 4 of x cosine 3x cosine x dx. Hopefully I will have enough space for me to write down my solution for this. And look at this. I'm going to apply integration by parts. I mean, again, from our previous example, we can see a hence in this particular question, which means that we're going to be making use of the previous result. And at the same time, I don't think it is very feasible for us to try standard results or to try fx, f prime x. It just doesn't seem to work for an x then with the other two trigonometric functions that are here. So we are going to be dividing this into two parts. Let me just rewrite it, although it is not very necessary. But I'm going to try to have an x and this to be the other part of the expression. So we have a cosine 3x cosine x dx, which means that I'm going to be getting u to be the one that is not so integratable. So like what we were saying, we will actually be focusing on dv dx in order for us to choose if I'm not applying the LIATE. So I'm going to go for dv dx to be this. Again, obviously, it's because I can already integrate it. So this is going to be equal to cosine 3x cosine x, and u is going to be this x. So for here, du dx is going to be 1, and v is going to be this over here. Let me just write it down. So from here, v is going to be equal to 1 over 8 sine 4x plus 1 over 4 sine 2x. And now I can re-express this, and then it seems to be a very tedious question. But I don't think it is that difficult for us, right? Anyway, I don't mind trying slightly more tedious questions now because I'm trying to get myself warm up to all this algebra that are involved in integration. So it's going to be uv. So it's going to be x of 1 over 8 sine 4x plus 1 over 4 sine 2x. And let's not forget about the lower and upper limit. So it's from 0 to pi over 2. Minus away v integration of v du dx. So minus away integration from 0 to pi over 2 of this times this, which is actually just going to be this because this is 1. So I have a 1 over 8 sine 4x plus 1 over 4 sine 2x dx. This is equal to, if I were to put pi over 2 in, we will have a pi over 2. We will have a pi over 2. Oh, actually, when I do a sine 4 times pi over 2, it is going to be a sine 2 pi, which is 0. And if I were to sub this in, we will have a sine pi, which is also going to be 0. So this is going to become 0 when I sub pi over 2 in. When I sub 0 in, it will also become 0. So I guess we will just be having a 0. So minus 0 pi over 4. Oops, I realized I've made a mistake. So let me correct my mistake. It is not pi over 2, this is pi over 4. So this is supposed to be pi over 4. Here is supposed to be equal to pi over 4. Let me correct this. Let's see whether we are still going to be getting a 0. So if I were to sub pi over 4 in, we're going to have a sine pi. Sine pi is 0. If I were to sub pi over 4 into here, we are going to have a sine pi over 2, which is 1. So it will be pi over 4, 0 plus 1 over 4 times 1. So pi over 4 multiplied by 1 over 4. Subbing 0 in is still going to be getting us a 0. So I have this, minus away this. Again, this is an easy integration because it's already following standard enough results for us to apply fx f prime x. So this is going to be equal to 1 over 8 times 4, it is 1 over 32. Then minus cosine of 4x. So minus, let me write it in front. So I have a minus 1 over 32 cosine of 4x. Similarly for this, it is going to be minus 1 over 8 cosine of 2x from 0 to pi over 4. So this, I have a pi over 16. Minus away, I'm going to introduce pi over 4 into here, which gives me a cosine pi. If I were to introduce that in, cosine pi is going to be equal to minus 1. So we will have a minus 1 over 32. Then substituting this in is going to give me a 0 because I'm going to have a cosine pi over 2. Cosine pi over 2 is 0. So the first term is going to be this. Then minus away, substituting 0 in, cosine 0 is 1. So here we have a minus 1 over 32. Cosine 0 is 1, minus 1 over 8. And if you were to evaluate this, you're going to get a pi over 16 minus 3 over 16, or we can also write this as pi minus 3 over 16. Okay, it is sort of tedious. And my apology for writing this wrongly. It should be pi over 4. In case you didn't capture it, I wrote this as pi over 2, so that's my mistake. Next, B. B, we need an improvisation. Because we are supposed to, according to what B require, we are supposed to integrate an expression that has a modulus. And let's not forget about the limitation of our integration technique. We don't know how to integrate something with a modulus. So we need to find a way to remove the modulus by doing a bit of improvisation. It's an easy improvisation usually for students. The problem is more of like when students didn't recognize that they cannot integrate something with a modulus and they just keep trying to find some techniques to integrate the modulus, but we can't do that, okay? So we need to improvise. How are we going to improvise? I'm going to start that by sketching the graph of whatever that is there, but without the modulus. I think that helps for this question. Let me show you. I'm going to sketch the graph of y is equal to x of x minus 2a. It is an easy graph to sketch. It is a parabola, a smiley face parabola, because the coefficient of x squared is positive 1. So this parabola is going to be something that is like this, and it's going to be cutting the x-axis at 2 points. One is going to be at 0, the other one is going to be at 2a, and especially when the question tells me that a is a positive constant, so I know 2a is going to be on the right hand side of 0. And for the integration that we are trying to work on, we are trying to integrate from minus a all the way till a of the modulus of this, modulus of x minus 2a dx. So on this, where is minus a and where is a? Minus a will be somewhere here, minus a, and a is going to be somewhere here. A is going to be here. And the more when we do a modulus to this, that means for this portion, it is going to be flipped up. So it's going to be this, flipped up. And if you were to try to see this from the perspective of definite integral, it is actually pretty much related to the area between the graph and the x-axis. Area between the graph and the x-axis. So we are looking at the area that is from minus a to a of the graph, which is the modulus one. Let me just draw in black color. The graph that is in the black color one is the one that is modulus. So this is y is modulus of x minus to a. And if you can remember, of course you will, it is from minus a to 0, this portion of the graph. Okay, I cannot really reach the other part here. This portion of the graph is the area that is between the original graph and the x-axis, which means that if I were to focus on just the area, because the area that represents this is going to be this region and this region. So if I were to focus on just this region, I can then re-express this partially into minus a to 0. For this area, it is integrating x minus 2a. And then as for this portion over here, it is reflecting this, which is from this graph, about the x-axis. So if it is reflected about the x-axis, it is going to go through a transformation where the new graph is going to be multiplied by negative, which means that just for this part, just for the top portion of the graph, it has a equation of minus x minus 2a, because it is a reflection of the original graph. And that is why for the other portion, minus a to 0 is going to be for this without the negative. But from 0 to a, we are going to write it as from 0 to a of minus x minus 2a, in order for us to get this area over here. So now we have managed to remove the modulus through our improvisation by making use of a graph. Okay, that is a very, very good idea. So by default, I do think that if we can use a graph to do a bit of improvisation to remove the modulus, we definitely should do that. We have another modulus question later, and I'm going to show you how we can do that without using graph. Okay, but graph is definitely one of the best possible ideas, one of the best possible strategy to manage modulus in an integration. Anyway, this is going to be very, very easy to integrate. So you'll be integrating from minus a to 0. We'll just do a minimal manipulation because I can very easily make use of standard results to integrate this negative. I'm going to take it out from 0 to a, multiplying this in x squared minus 2ax dx. So we have x to the power of 3 over 3 minus ax squared from minus a to 0. Minus away similarly for this, x to the power of 3 over 3 minus ax squared from 0 to a. So substituting 0 in, we're going to be getting a 0. Then minus away minus a to the power of 3 over 3 minus a to the power of 3. Minus away, substituting a in, we have a to the power of 3 over 3 minus a to the power of 3. Substituting 0 in, it is going to be equal to 0. And if you were to evaluate this, you will end up with 2a to the power of 3. And hopefully, so far, you are really getting a good warm-up to integration, because we're going to be doing questions that are going to be a little bit more tedious, a little bit more challenging. Okay, but I believe that once we are warm up, it is easy for us to continue to try our improvisation. But please make sure, okay, we are going to be sticking to our strategy here. And the more we can practice, the better it is definitely going to be during the exam. Question number 4. We have this. From ACJC. Part 1. We are going to integrate x over 1 plus x squared dx. I'm going to apply fx at prime x because I see the possibility that by letting fx be equal to 1 plus x squared, then f prime x is just going to be equal to 2x. So this is going to be 1 over 2, integration of 2x. Then this will be 1 plus x squared to the power of minus 2. So we have a half. Now fx, f prime x, this is 1 plus x squared to the power of minus 1 divided by minus 1 plus c. So we have a minus 1 over 2, 1 plus x squared plus C. We will need this result. Okay, actually this question is one full question by itself where when we are doing part 4, we are supposed to be making use of all the results that we have derived so far. But I don't think I'll have enough space to just leave everything here. So the result of this is here, okay? Let's make sure that we take note of this because we are going to be making use of this again. Part 2. By using substitution. By using substitution, x is equal to tangent theta is the equation that is given to us. And we are supposed to substitute and replace all the x that is in this integral here. So 1 over 1 plus x square. We are supposed to integrate this and show that it can become an expression that is like this. So we are going to be replacing all the x. I'm going to find first dx d theta. Dx d theta is secant square theta. This is an indefinite integral, so I'm ready to do all the substitution. We have a 1 over 1 plus x square, tangent square. Dx is going to be replaced by secant square theta, d theta. And 1 plus tangent square theta is secant square theta. So we have a 1 over secant square theta square. Secant square theta d theta. So we have a secant 4 theta, secant square theta. Cancelling them, it is going to be 1 over secant square theta d theta. And secant is 1 over cosine. So I can just write this as cosine square theta d theta. And this is very, very easy to integrate because we are going to make use of one of the most used trigonometric identity, the double angle formula. Cosine 2a is 2 cosine square a minus 1, which means that cosine square a is going to be cosine 2a plus 1 divided by 2. So I'm going to replace this by cosine 2 theta plus 1 divided by 2 d theta. 1 over 2, I'm going to just take it out, so I'm going to be integrating this plus 1 d theta. This is going to be equal to half. Integrating this is an easy integral. This is going to be equal to 1 over 2 sine 2 theta, then plus this. This is going to be theta, then plus c. Let's not forget that we are supposed to re-express this, which is in terms of theta now, back to an expression that has x, especially the question wants us to show that it is in terms of x. I think this is fine because for this, I can just simply take this and rework this to tangent inverse x. So I'm going to be replacing this theta by tangent inverse x. It is going to be part of the expression that we're going to be showing already. But for this, we need to show that this can become something that is like x over 1 plus x squared. So I'm going to make use of another trigonometric identity, another double angle formula, which is sine 2a is 2 sine a cosine a. So if I were to replace this by 2 sine theta cosine theta, the 2 and a half can be cancelled. I'm going to be left with a half of sine theta cosine theta plus theta plus c. And sine theta cosine theta, I think I can do the replacement by drawing for myself a right-angled triangle. I think that is very, very useful for this particular kind of question. So if I were to just focus on this and draw a right-angled triangle to this, then tangent theta is opposite over the adjacent. I can see x as x over 1. So it's going to be x over 1, which means that here by applying the Pythagoras theorem is this. So this is going to be equal to half. Sine theta is opposite over this. So it's going to be x over square root of 1 plus x squared. Cosine is this over this. So it's going to be 1 over square root of 1 plus x squared. And this, I can replace it by tangent inverse of x, then plus c. So I guess I've gotten my answer. It is equal to half of x over 1 plus x squared, because square root of this times square root of this, the square root will disappear. And this is going to be this plus tangent inverse of x plus c. So by comparing this to what I'm supposed to show, k is equal to this number, k is equal to half. So this is part 2. And hence the question says, by making use of part 2 where k is equal to half, I'm going to erase this so that I can create some space for myself to do part 3. Hence the question says, we are supposed to integrate that. You know, when I was looking at this hence question, I was thinking, okay, maybe I'm going to try to make use of integration by parts. I seriously thought about that because the question says hence, and we have done a few questions, and it does seem like hence is a good strategy. By part seems like a good strategy to use based on the experience that we have. But let me just show you, okay, when I try by parts for this, I sort of like fail. Part 3. We are supposed to integrate this x squared over 1 plus x squared dx. And if I were to attempt to do by parts by making use of, let's say, part 2. If I were to try by parts by making use of part 2, then it seems like I can rewrite this as maybe an x squared, which can be integrated, then a 1 over 1 plus x squared dx. So this is probably going to be my dv dx. This is going to be u if I were to apply integration by parts. Or I can also have another version, which is if I were to write this down as just simply an x, breaking down this x squared into 2 parts. So it is an x and also a x over 1 plus x squared dx. Then I can make use of the first part to do my integration by letting dv dx be equal to this and using first part of the result from the first part that we have done. Then I can integrate this, and this can definitely be differentiated if I were to let u be equal to this. So I feel that this question really try to push for students to think through the possibilities and options in order for them to perform an integration. And I mean, I tried this, submitting to you very, very honestly, and I know that I was wrong because, maybe in the end I may be able to get the answer, but I don't think this is going to be efficient enough for me to handle this during an ACJC exam. But the thing is, for integration, other than using the default strategy first, trying out the default strategy first before applying integration by parts, one other very, very useful tip that I want to give you guys is that you should whenever you are stuck, especially when you are trying to find an option to integrate, it is okay. Your aim is to do a bit more experimentation. Your aim is to try a bit more improvisation in order for you to find different ways to move on in your integration. It is part and parcel of the entire H2 Math anyway, to do exploration, to do a bit of trial and error. So if you have had tried this, maybe some of you should really go and try to see whether it is going to work and compare to a shorter version of the solution, which is if I can just think of a way to algebraically manipulate this. Let me show you a possible way to manipulate this. If I were to algebraically manipulate this, I can actually try to create a 1 plus x squared in the numerator. So 1 plus x squared. So I created a 1 by adding a 1, so I need to minus away a 1. And I'm going to make this into a term by itself, divided by 1 plus x squared dx. So if I were to take this divided by this, I'm going to be left with a 1 over 1 plus x squared without the square. So if I were to take this divided by this, it is just going to be this. Then we will have a 1 over 1 plus x squared, which I can then make use of the result from part 2. So how do I know that I'm supposed to do this? Basically, we can't. But what we can do is, if I were to try some other strategies at least when I'm practicing, I don't mind switching strategies. I just want to independently do explorations as much as possible. I think all this gives us strength in order for us to find a way to navigate through an exam question independently during an actual exam. This can be integrated because I can make use of my ML26. I'm seeing 1 as if it is a 1 square. Then this will be tangent inverse of x. Minus away this, which can also be integrated because we have the result from the previous part, which is part 2. And that gives me this as x over 1 plus x squared plus tangent inverse x plus c. So tangent inverse x minus half of tangent inverse x gives me a half of tangent inverse x. If I were to combine this together, it is going to be half of, here we will have a tangent inverse x, that minus x over 1 plus x squared plus c. And finally, part 4. Use all of the above results. We are supposed to find this new integral. I'm going to erase this, but I'm going to still make use of this result. In fact, I'm going to be making use of the results from part 1, part 2, and part 3 to do part 4. Part 4. We are supposed to integrate this x squared plus 2x plus 5 divided by 1 plus x squared square. For this, I think the manipulation is easy. I will just break it up into 3 separate fractions. First is this x squared over 1 plus x squared square, which I can make use of the result from part 3. Then the other one is going to be plus 2. I'm going to take it off the integration notation. We will have a x over 1 plus x squared square, which I'm going to make use of part 1, the results from part 1. And finally, it is going to be this 5 over this, where 5, which is a constant, I'm going to take it off the integration notation. We will have this square, this. And this, I'm going to make use of my results from part 2. So, it's going to be a long answer here. It is, for this, it is going to be equal to half of tangent inverse, making use of part 3's result, minus away x over 1 plus x squared. Then plus 2 times of this, I'm going to make use of the result from part 3. And this is going to be equal to, from part 3. This we are using part 3. We are using part 1's result. And part 1's result gives me this as minus 1 over 2 of 1 plus x squared plus 5 times of this, which I'm going to make use of part 2's result, which is going to be multiplied by half. Then we will have a x over 1 plus x squared plus tangent inverse x. So I have this plus c, and if I were to just consolidate all the tangent inverse x together and grouping all the rest of the algebra together into one single expression, you are going to end up with this 3 tangent inverse x plus 2x minus 1 over 1 plus x squared plus c. Let's check out another one, question number 5. Question number 5, part 1, the first part, we are supposed to differentiate tangent square x. So of course, tangent square, if you are comfortable, you can just differentiate it directly. If not, it is definitely also possible to just re-express this as tangent x square before we differentiate. So it's going to be 2 tangent x to the power of 1, which is just tangent x. Chain rule, differentiating tangent, it is going to give us a secant square. So we have this secant square x. And the question says, hence, by making use of this, we are supposed to hence integrate this. Let's try integrating from 0 to 1/4 pi from diamond high, secant square x, tangent x, then e to the power of tangent square x dx. And what strategy should we be using? Definitely not the backup strategy. or at least I won't consider the backup strategy first, okay? I mean, who knows? You know, if our default strategy fail, maybe I should be using my backup strategy. But our default strategy will work, especially when I can really tell that tangent square x, if it is going to be fx, then f prime x, which I've already gotten here, is just simply 2 tangent x secant square x, which can be generated here by adding a half, so that I can have a 2, then tangent x secant square x, which is our f prime x, e to the power of tangent square x dx. So we will have a half of e to the power of tangent square x from 0 to 1/4 pi. Substituting the numbers in, we have a tangent pi over 4 to the power of 2. Tangent power of 4 is 1. To the power of 2 is still going to be equal to 1. So we have a e to the power of 1. Minus away tangent 0 is 1. So e to the power of 0 is 1. My answer is this. This is part 1. Let's take a look at part 2. The question actually gave us some hint. We are supposed to re-express that. So let's do according to what the question says. Part 2, I'm going to re-express this according to what the question wants. So this minus 32x to the power of 3. I'm supposed to re-express it into 1 plus mx. So I guess we should try to factorize this. And I'm going to try to factorize out 8x. So if I were to do that, then I'm going to be left with 9 minus 4x squared. So I'm going to apply this to help myself integrate this. 1 plus 72x minus 32x to the power of 3 divided by the square root of 9 minus 4x squared, which is comforting because we are getting this 9 minus 4x squared here after I manipulated the expression from the numerator. And so I'm going to replace this 1 plus 8x, then 9 minus 4x squared divided by the square root of 9 minus 4x squared. So I can break this fraction up into 2 parts. One is this divided by this, divided by 9 minus 4x squared. And I can see the potential of integrating this using the standard result in fx prime x, specifically the one that will give us tangent inverse, the one that gives us sine inverse, right? So I'm going to rewrite this 9 as 3 squared, and this I'm going to write it as 2x squared, which is 4x squared. Then the x plus 8, I'm going to take out of the second integral, and we will have, in fact 8, I think it is a good idea to leave it inside. So let me just leave it inside first. It will be 8x, this divided by this, which is square root of 9 minus 4x. So we have 8x square root of 9 minus 4x squared dx. And I can see how this can be integrated because I'm going to be letting fx be equal to this 9 minus 4x squared, and f prime x is minus 8x. So I just need a negative here. So to introduce that, I'm going to put in a negative outside so that I can have a negative x here. So this square root, I'm also going to re-express it as this to the power of half. And now we have an fx, f prime x form that we can carry out our integration. So for this, it is going to be 1 over 3. Sorry, it's not 1 over 3. It's going to be 1 over 2 sine inverse of 2x over 3. Then minus away integrating this, it is going to be 9 minus 4x squared to the power of 3 over 2 divided by 3 over 2. And this plus c. Just doing a quick simplification to this, we will have a half sine inverse of 2x over 3 minus 2 over 3 9 minus 4x squared to the power of 3 over 2 plus c. We have 10 questions and we have already done 5. Okay, I think we are moving on at a good pace. Let's continue to practice. Let's continue to do the next few questions together with the aim of getting us so warm up to integration that maybe even for some of us, just after these 2-hour sessions, you will be able to tackle an exam question independently already. But just in case you are still not ready for that, it is fine. Continue to practice with your revision package for maybe another 1 hour or so. I believe that once you have finished this with all the practices, you should be able to independently score pretty well during your exam. Okay, just as I say this, I realize we are looking at a question that is potentially a bit like the ACJC question that we have just done. It requires us to do all those trial and error, and that is definitely not the kind of question that I like to see in an exam. But at the same time, if I don't mind doing a bit of trial and error, then in an exam, I will be able to display my strength in terms of being versatile enough to see and try out questions that I'm not so familiar with. For this Hwa Chong question part 1, when I was doing this, the first time I saw this was a question that was in SRJC. And I spent quite a bit of time doing my experimentation before I finally got it. Question number 6. We are supposed to rewrite secant cube x dx into the form of secant x, secant square x dx. And let me share with you what I've done. What I tried was to re-express secant square x into 1 plus tangent square x, because that's what I thought I should do. According to our default strategy, we should try to apply some trigonometric identities if it is possible. And that was my aim, to try to re-express it such that it can become one of the standard integrals for me to integrate. But even after I try re-expressing this into 1 plus tangent square, I failed to finish up my integration. And that is fine, because that is part and parcel of a typically more challenging integration question, which requires us to do all those trial and errors. So if our default strategy failed, we do have a backup strategy. So that was what I experienced here. My default strategy failed. So what is the backup strategy? Is to make use of integration by parts. And for integration by parts, we cannot decide using LIATE again here. So I'm going to decide based on whichever one that I think is easier for me to integrate. And sadly, I can actually integrate both. I can integrate secant, which I have a formula that is inside my MF26. I can also integrate secant square. So I need to choose one. In fact, when I was trying out this, I chose this because it's easier to integrate. But I mean, this is going to get me my answer. I'm going to show you my solution now. But I mean, for some of you, you can definitely try to let dvdx be equal to secant x and just experience for yourself, okay? Regardless of whether it is going to work or not, just experience for yourself this trial and error process. I think it's going to be a very, very good practice. So I'm going to go for this, and secant x is going to be here. So for this, du dx differentiating secant x is going to be secant x tangent x. And for this, integrating this, it is just going to be simply tangent x. So now this can be re-expressed as uv. So it is going to become secant x tangent x minus integration of v du dx, which is going to be secant x tangent x times tangent x tangent square x dx. So integration by parts is once again not helping me to conclude my integration. It is adding a comma to my statement. So I'm expected to continue to integrate this. So I'm going to use the same set of strategies again, which is I'm going to try to use trigonometric identity some more. And in case all fail, then maybe I'm going to try another round of integration by parts. So if I were to do another round of trigonometric identity, I'm going to try to replace this by secant square x minus 1. So let's try and see what we are going to be getting. So we will have this minus, this is secant x, and this is secant square x minus 1. In fact, I can see the potential of us integrating this already, because we have this, then this is going to be secant cube x. which reappears again, right? It reappears, whatever that we were supposed to integrate reappears again here. Then this is going to be plus integration of secant x dx, which can be integrated. Yeah, I'm going to just use the formula that is inside my MF26. So let me rewrite this whole statement, which is integration of secant cube x dx is equal to secant x tangent x minus integration of secant cube x dx. Integrating this is ln of secant x plus tangent x. And this, I'm going to shift it over to the left-hand side. To combine it with this, giving me 2 of secant cube x dx. And this is secant x tangent x plus ln of modulus of secant x plus tangent x plus, I'm going to just go for an a first because I know I'm going to be dividing this across to the other side, then I'll replace that whole thing by c. So now it is going to be secant cube x. I can conclude, I can add a full stop to my statement already. It is going to be equal to half of this. So it's going to be half of secant x tangent x plus ln of modulus of secant x plus tangent x plus a over 2, which I'll just simply write it as c. Hence, the question says, hence we are supposed to evaluate this again, but as a definite integral. So I'm going to just leave my result here for me to make use of. And let me just rewrite the integral that is here. We are supposed to be integrating this from 0 to tangent inverse of 2. And we are supposed to find the exact value of this, or else what should we do? We should just press this into the calculator, right? So this is going to be, let me make use of this result, and how I wish I can just cut and paste. Okay, but I'm going to just write it down. So it is going to be half secant x tangent x plus ln of modulus secant x plus tangent x, and close bracket. This is going to be from 0 all the way until tangent inverse 2. We need the exact result. So to get the exact result, I guess this tangent is fine if I were to substitute tangent inverse 2 in, because tangent inverse 2, this is going to just get me a 2, this is going to get me a 2. But the problem is this secant x. How am I going to evaluate this secant x? So what I think I'm going to try and do is, because I know this is a value for x, so I'm going to try the triangle strategy again. I'm going to draw a triangle to try represent secant x. That means if I were to let x be equal to tangent inverse 2, that means tangent x is going to be equal to 2. Sketching my triangle, the right angled triangle, this is x, 2 is like 2 over 1. So this is going to be square root of 2 square plus 1 square, square root of 5. Which means that from here, secant x, I'm going to work out a cosine x. Cosine x is going to be 1 over square root of 5, which means that secant x is going to be square root of 5. So substituting this in, we are going to be having a secant x, which is square root of 5. So half of square root of 5. Tangent inverse 2 is 2 plus ln. This is going to be square root of 5. This is going to be 2. It is a positive number, so we can remove this modulus, replacing it with a curved bracket. Then minus away, we have a half of this. If I were to substitute this in, tangent 0 is already 0. And if I were to substitute this in, tangent 0 is 0 and secant 0 is 1. So ln 1 is 0. So here I'm going to be left with just a 0. So my final answer is going to be this times this is square root of 5 plus half of ln square root of 5 plus 2. Okay, that is question number 6. Let's try the next one. question number 7. Question number 7 is, it looks a little bit strange because we have that n that is inside the integral. But I think it is actually not too bad. So part 1. Integrating n cosine inverse of nx dx. Now for this, I'm going to just use integration by parts. Why? Because from our experience in integration by parts, we do know that whatever that is a single trigonometric inverse or logarithmic function, it is usually going to be integrated using integration by parts. Furthermore, there's no standard results that can help me to integrate this. There's no fx f prime x that I can find in this case in order for me to integrate. That is why my default strategy should have already failed, and that means I have to make use of my backup strategy. So we are going to let u be equal to cosine inverse nx, and I'm going to just let dv dx be equal to either 1, or maybe I can just let it be n. N is a constant, it's a positive constant. So du dx, this is going to be minus n over square root of 1 minus this square, which is n square x square, and v is going to be equal to nx. So this is going to be re-expressed into uv. So we have a nx cosine inverse of nx minus away integration of this multiplied by this. The negative, if I were to take it out, it is going to become positive. So, okay, I'm going to leave the negative there, okay, because I realized that we will actually be doing fx f prime x later, and I will need that negative. So I'm going to leave this negative here. So we have a negative n square x over the square root of 1 minus n square x square dx. And I'm going to apply fx f prime x here because fx is this 1 minus n square x square, and f prime x is going to be minus 2 n square x. And we're going to create the 2 here by dividing by a 2 outside. This is equal to nx cosine inverse of nx minus away half, so that I can create a 2 n square x, 2 n square x in the numerator. For the denominator, shifting up to the numerator by making use of indices, I can re-express this as this. And now we have a fx f prime x form. So this is nx cosine inverse of nx. Then this is going to be minus half. Integrating this is this square to the power of minus half plus 1, it is half, divided by half, then plus c. So my final answer is going to be nx cosine inverse of nx, half will disappear, minus away this, which is square root of 1 minus n square x square plus c. Hence, we are supposed to find the exact value of the integration of this again, but now with a definite integral. So in part 2, it is integrating this from 0 to 1 over 2n. So we're going to be making use of this set of results here. Let me erase this. So for this, I can now make use of this result, and I still cannot do cut and paste, so I'm going to just write it again. And x, then cosine inverse nx minus away square root of 1 minus n square x square from 0 to 1 over 2n. Let's substitute the numbers in. So we have this multiplied by this, n times 1 over 2n gives me half. Cosine inverse of half. Minus away, I have a square root of. This is going to be square root of 1 minus 1 over 2n squared will give me, square of 1 over 2n squared gives me 1 over 4n squared. N squared and square can be cancelled. I'm going to be left with a 1 over 4. So I have this. Then minus away, substituting 0 in, this is just going to become 0. And substituting 0 in, I will have a square root of 1. So it is going to be minus square root of 1, so minus 1. So we have a half. Cosine inverse half, that is pi over 3. Minus this is square root of 3 over 4. Then we have a minus 1 plus 1. So my final answer is going to be equal to pi over 6 minus this. I can also rewrite it as square root of 3 divided by square root of 4, which is 2, then plus 1. Question 8 from NYJC. Let's take a look at this. Question 8. Oh, okay, we have another modulus. So for A part 1, we are supposed to integrate 2x minus 4 divided by x squared, 2x plus 4 dx. We are supposed to integrate this, and I guess we are going to do some algebraic manipulation, like the kind of manipulation that I've written here. We can be doing long division. Do I need to do long division for this? No, I don't. I don't have to, because it is already a proper fraction. Can we do a partial fraction to this? Because if I can, I should try to do a partial fraction. It is usually going to be easier, but sadly, I don't think I can very easily, I don't even think I can factorize this into two linear expressions in the numerator, in the denominator. So partial fraction is not exactly going to work. So I'm going to continue with my manipulation by trying out the fx, f prime x. In fact, this is a common enough question. I'm very sure you have seen this in your tutorials before, and definitely it should appear in some of the revision package. So whatever that I'm doing here on the board is a result of my experience that is accumulated through doing more of this kind of questions in the previous questions, and also doing all the trial and error that was initially necessary, but because I've acquired experience, so it gets faster and faster, and I don't have to do so much trial and error. And all these are achieved through practice, okay? So if you have been practicing, then looking at this, what we can try do is to do fx, f prime x. So f prime x is 2x minus 2, and I believe that I can try to create this 2x minus 2 here in the numerator. Actually, it is very, very simple. It is just breaking up this minus 4 into minus 2 divided by x squared minus 2x plus 4 dx. And if I can just break this up into two parts, now for the first part, we have 2x minus 2 divided by this 1 over x squared minus 2x plus 4. And this I can apply fx, f prime x. Minus 2, if I were to take it out, I will have a 1 over this. And when we have a constant over a quadratic from experience, okay, or else you will be doing some trial and error. So from experience, I know one manipulation that I can try, according to what I wrote there also, is completing square. So instead of just writing this, I'm going to complete the square to that, which is going to give me a x minus 1 square plus 3. And this, we can actually apply fx, f prime x. And I'm going to be applying the one that gives me tangent inverse, because 3, positive 3, I can see it as square root of 3 square. So for this, we have a ln of modulus of x squared minus 2x plus 4, which if you were to just complete the square for this expression, you're going to be getting this. And this expression is a always positive expression. So if you manage to recognize that, it will be a bonus, although it is not going to get you extra marks, but it's probably going to give you a bit of favor because you are algebraically more sensitive, that you can manage to recognize that this expression here is always positive expression. Minus 2 of 1 over square root of 3, tangent inverse of x minus 1 over square root of 3 plus c. I probably should just write the 2 here, okay? So I have this as my answer. And in part 2, so we have the answer already. Let me just write it down here. I'm going to be making use of part 1 to do part 2, since the expression looks so similar except that there's this extra modulus. So this is equal to ln of x squared minus 2x plus 4 minus 2 over 3 tangent inverse x minus 1 over square root of 3 plus c. And I'm going to make use of this result to integrate part 2, which comes with a modulus. Part 2. It comes with that modulus, and I'm doing a definite integral from 1 to 4, modulus of 2x minus 4. This is going to be divided by this, plus 4 dx. Ideally, I would like you to sketch the graph like how we have done it just now. Sketch a graph without the modulus, then impose the modulus. You can also sketch the graph with the modulus, and then by doing a comparison, breaking up the graph into different parts and different regions, just like how we have done it, then you try to re-express this integral into the individual regions, in order for you to remove the modulus from the integral. But for this particular question, it says without the use of a graphic calculator. So I do think that if we were to use graph, it is going to be a little bit tricky to try to hide the fact that we have used graph. So I'm going to make use of something else. It is one of the sessions that we did a few weeks ago on modulus function, which I was trying to say that modulus function is actually which is actually a function that is tested more often in our exams than what a lot of people thought. That is why not a lot of schools, talk about modulus function, but I'm glad we have spent one session of probably 1 plus hours on modulus function. And I can already see that some of you who previously didn't know how modulus function can be properly managed in questions, and those questions that we did are like integration, are like functions question. Now you know how to do it. Okay, so I'm proud of you if you are already able to apply that. But in case you have not been able to apply that, or you didn't get a chance to apply that, seeing what I'm trying to do here reminds you that we have done it previously, go and take a look at the modulus revision that we did. So for the modulus revision that we did, we based it, if I cannot draw the graph, we can base it on the definition of modulus function. I'm going to write down 2 of the definitions. One is the one that can actually be found in your secondary school's A-Math textbook, which is modulus of x, which is a function. It is a piecewise function where modulus of x is going to be x. If x is bigger or equal to 0, it is going to be minus x if x is less than 0. I can also replace this x by a more complicated compounded version of x, for example, fx. So it is going to be the same way to look at this modulus function, which is if fx is a positive function, then the modulus doesn't really matter. So this is if fx is bigger or equal to 0. But I'll add a negative to fx if fx happen to be less than 0. I'm going to try that to analyze this 2x minus 4. So I'm going to analyze when this 2x minus 4, which is like the fx here, is positive, when is it going to be negative. So if I were to do this analysis, I'm going to let modulus of 2x minus 4 be a case where it is bigger or equal to 0. So I'm letting the expression that is inside the modulus. So 2x minus 4, I'm letting it be bigger or equal to 0. This tells me that x is supposed to be bigger or equal to 2. And if I were to let 2x minus 4 be less than 0, if you were to be a case that is like this, then this tells me that x should be less than 2. So I can try to apply that here now because I'm trying to integrate across this graph from 1 to 4. And from 1 to 4, if I were to know that the moment when x is less than 2, this expression here is negative. So if I were to integrate from 1 to 2 instead of all the way to 4, I'm integrating from 1 to 2. This expression is negative, so I'm going to add a negative to it. I have this divided by x squared minus 2x plus 4. Then I'm going to integrate from 2 to 4. So x is now bigger or equal to 2. So this expression is going to be a positive expression. So this is just going to be 2x minus 4, as it is without having to add in an extra negative. So we have a x squared minus 2x plus 4 dx. And now we are ready to make use of the previous result, and it is going to be one tedious process of substitution. So this negative, I'm going to take it out, and integrating this, it is just going to be making use of this result. It is going to be equal to ln of x squared minus 2x plus 4 minus 2 over 3 tangent inverse of x minus 1 over square root of 3 from 1 to 2 plus this, which is going to be, again, this ln x squared minus 2x plus 4 minus 2 over 3 tangent inverse of x minus 1 over square root of 3 from 2 to 4. And let's do the substitution. It's going to be minus of. It's going to be minus of. Here is going to be, if I were to sub 2 in, it will be 2 squared minus 2 times 2 plus 4 is going to be 4. So ln 4 minus 2 over 3, 2 over 3, tangent inverse of 1 over square root of 3. So I will be getting a special angle pi over 6. So I will have this, then minus away, substituting 1 in, it will be 1 square minus 2 plus 4. So we will have a ln 3. Substituting 1 in, 0, tangent inverse 0 is going to be 0. So the second one is going to be this. Then plus, now if I were to sub 4 in, I will be getting a ln 12. Then minus 2 over 3, tangent inverse of 3 over square root of 3, which is square root of 3. Okay, I'm going to be getting a pi over 3 here. Then minus away, this I will have a ln 4, basically is just repeating this, minus away 2 over square root of 3, 2 over square root of 3. Did I write anything wrongly? Oops, I realize I've made another mistake, which is this. We have made a mistake in the previous part. Please help me to correct that. It is not 1 over 3. When I do a tangent inverse, it is 1 over square root of 3. So it should be a square root here. Okay, previously when I integrate the, let me just write it down, okay, just to do my correction. So I did this 1 over, we had a x minus 1 square plus 3, which I wrote it as this, and square dx. So I made a mistake. I wrote it as 1 over 3, but it should be 1 over this, which is 1 over square root of 3. Then tangent inverse of x minus 1 over square root of 3. And there was a 2 in front, so multiplying it by 2 give me this 2 over square root of 3. So I made a mistake here. Please help me to correct it. It should be square root of 3. So here, it should also be a square root of 3. The same for this. It should be a square root of 3. So here, it should be a square root of 3. So here is now square root of 3. So this tangent inverse of 1 over square root of 3. And if you were to simplify all this, okay, I'm going to leave it to you to simplify, okay? If you were to simplify all this, you actually end up with quite a nice number, which is this, which you can also write this as this 3 over 2 square. So 2, if you were to bring it forward, you have a 2 ln 3 over 2. Next, let's try B. B, we are supposed to differentiate first. Then after that, we are going to integrate. And let's see whether we are actually going to be looking at an integration by parts question. Because according to what we have experienced so far, when we have a question that is like this, usually it ends up with a by parts. So let's see whether this question is setting up a by parts scenario for us. Let's differentiate. Oh, we are not even asked to differentiate. We are already given directly that differentiating 1 over cosine square x. This is 2 sine x divided by cosine cube x. Oh man, we should have, I mean, it could have even been better for us if we were to differentiate this because it's so easy to differentiate. You know, I just need to re-express this as cosine x to the power of minus 2. Then we can do our chain rule. And with this that is given, we are supposed to evaluate from 0 to pi over 4 of sine square x over cosine cube x dx. And we need to do that exploration that I was trying to say. We need to try to see how I can make use of the previous part here. And since we need to make use of the previous part, of course we should try a little bit of trigonometric identity if this is not given. Okay, we should have tried that. But because this is given, I'm going to change my strategy to see whether I can adopt integration by parts to manipulate this first. Okay, and it is because of the structure and the format of this particular question. So if I were to be trying that, then I need a 2 for me to analyze. So I'm going to add a half outside so that I can introduce a 2 in. And I'm going to break up this sine square into 2 parts so that I can have a sine in the numerator. So it will be a sine x as a term by itself. The other one is going to be 2. Then sine x over cosine cube x dx. I'm going to try and see whether this is going to work. So one is going to be u, the other one is going to be dv dx. And for those that I'm choosing by myself instead of using the LIATE, I'm going to choose based on the one that can be integrated. So I'm going to choose based on dv dx. And I'm going to go for this definitely because this came out by, this was given to me by the question. So for this, v is just going to be 1 over cosine square x. As for u, I will have it as this. And du dx is equal to cosine x. So this, I will have a half of uv. So it is going to be equal to this sine x over cosine square x from 0 to pi over 4. uv minus integration of v du dx. So it's this times this. So this times this, actually cosine and cosine can be cancelled. I'll be left with a 1 over cosine. So 0 to pi over 4, I have a 1 over cosine x. And this is very easy to integrate, right? Because this is just going to be secant x. And we have a formula for secant x. This is equal to half. We can substitute this in later, or we can also do that now, definitely. If I were to substitute this in now, we have a 1 over square root of 2 divided by 1 over square root of 2 square. We will have a 1 over 2 in the denominator, and numerator is this. If I were to substitute 0 in, sine 0 is going to be 0. So we will have this. Minus away this is just, let me rewrite this cosine as secant x dx. So we have a 1 over 2. This divided by this is 1 over 2. So this divided by this, in fact, I think it is a good idea to just multiply in. So half and half can be cancelled. I'm going to be left with a 1 over square root of 2. And this times this minus half. This is going to be just ln of secant x plus tangent x from 0 to pi over 4. So we have this as 1 over square root of 2 minus away 1 over 2. And if I were to now substitute the numbers in, we will have a ln of secant pi over 4 is going to be square root of 2. Then tangent pi over 4 is going to be 1. And this is always positive, so I'm going to just put an overall modulus. I'm going to just put, without the modulus, but I'm going to just put the overall curve bracket. 0, when I sub in, this is 1, and this is going to be 0, so ln 1 is going to be 0. So I will basically be taking this minus away 0. So my final answer is going to be 1 over square root of 2 minus 1 over 2 ln of square root of 2 plus 1. Next, let's take a look at question number 9. Here. SAJC. This is an interesting question. It is a little bit similar to one of the questions that came out in the A-levels. Part 1, we are supposed to integrate e to the power of x cosine nx. My default strategy should fail. Okay, I don't think I can apply any. I mean, this is definitely not a standard result. So I'm going to think about fx, f prime x, and I don't think it's going to work. That is when we are going to introduce integration by parts. And I'm going to apply LIATE. So for what we have here, we have e exponential, t trigonometry. So LIATE, t comes before e. So I'm going to let u be equal to cosine nx and dv dx be e to the power of x. Differentiating this, du dx, this is minus n sine nx. And v is e to the power of x. So this can be re-expressed as uv. It will be e to the power of x cosine nx. Minus minus becomes plus, and n, I'm going to take it off the integration notation. So it will be minus n plus n. Then we have e to the power of x sine nx dx. And I'm going to apply integration by parts again. With experience, some of you probably can already be expecting what is going to happen here. The integral will repeat. And to a certain point of time, it will repeat to this that will appear on the right-hand side. Then I'll combine this just like how we did the Hua Zhong question just now. So I'm going to go for another round of integration by parts. U is going to be equal to sine nx. And dv dx, this is e to the power of x. Du dx is n cosine nx. And v is e to the power of x. So this is e to the power of x cosine nx plus n of uv e to the power of x sine nx minus integration of v du dx, which is minus n integration of e to the power of x cosine nx dx. And this is where it starts to repeat again. Let me just rewrite this into one full, just side by side. So we will have an integration of e to the power of x cosine nx dx. This is equal to e to the power of x cosine nx plus n e to the power of x sine nx minus n squared. This times this minus n squared integration of e to the power of x cosine nx dx. And I'm going to bring this over to the left-hand side to combine with this. So I will have a 1 plus n squared as the coefficient of e to the power of x cosine nx dx. Let me just take a look. Okay, I realized the question didn't put a bracket, so I'm not sure even why I suddenly put a bracket here myself. Okay, so anyway, that doesn't matter. This is equal to, I will have this as e to the power of x. I will have this. Then, oh, okay, for some reason I wrote this in another way, but okay, I'm going to just rewrite this. I think that is because SAJC's solution wrote this first. So I'm going to just write this first also. It doesn't matter even if you have to write this first. So this is going to be equal to n e to the power of x sine nx. Okay, I'm doing the bracket thing again. I'm going to remove this bracket. So nx plus e to the power of x cosine nx. Cosine nx. There should be a plus c. I think I'm going to just put it as a plus a for now. Then dividing this across will get me my final answer, e to the power of x cosine nx dx is equal to this divided by 1 plus n squared. And I'm going to just adopt the final answer that was given by SAJC during that year. So they factorize out this n e to the power of x. So if I were to factorize out this also, then we will have sine nx plus cosine nx divided by n. Okay, this is not necessary. You can just do whatever simplification that you want because you cannot possibly know that the answer looks like this. So this 1 plus n squared plus a divided by 1 plus n squared, which I'm going to let it be c. So this is the answer that we have gotten for part 1, and hence without using the calculator, we are supposed to integrate this again, and this time it is a definite integral. Part 2. It is a definite integral from pi to 2 pi of this, and we have the result here. And this is the one that actually appears in one of the A-levels in the recent years, because we are supposed to do a bit of a deduction. Okay, I'm going to show you how that is done. So we will have this, and I'm going to just take out this n over 1 plus n squared, which will leave me with e to the power of x, then sine nx plus cosine nx over n. So we have this from pi to 2 pi. I'm basically using this result, but I factorize out n over 1 plus n squared, leaving the e to the power of x inside. So we are supposed to evaluate this, which is actually not very possible, but the question actually gave us a condition which makes the evaluation possible, and the condition is that n is an odd number. So we can actually evaluate it to a fixed value. I'm going to show you how that can happen, or at least I want to show you what is the problem that you will face when you're doing the substitution. So this is going to be equal to n over 1 plus n squared. And I'm going to substitute this in, so we have a e to the power of 2 pi. Then we will have a sine of x is 2 pi, so we have a 2n pi. Then plus cosine of 2n pi divided by n, minus substituting pi in, we have a e to the power of pi. Then we have a sine n pi plus cosine n pi divided by n. We have this. I don't think we need to do much about this e to the power of 2 pi and e to the power of pi, but we can do something about this, and this. You can either use graph, or you can just write down a few values for you to try see the pattern. What do I mean by write down a few values? For example, this sine 2n pi. So if I were to work on sine 2n pi by itself, n is an odd number. Okay, according to what the question says, n is an odd number. So I'm going to try a few odd numbers. For example, if I were to let n be equal to 1, then we will have a sine 2 pi, and that is 0. N is equal to 2. We have a sine 2 times of 2 pi, and this is also 0. Sorry, n is an odd number, so 3. So 3 times of 2 pi, this is also an odd number. Then if n is equal to 5, then we have a sine of 5 times of 2 pi, and this is also equal to 0. Basically, it is just sine of multiples of 2 pi, which is always going to be equal to 0. So we are seeing this pattern happening. So we know this is going to be evaluated to be 0. And let's try to do an analysis for cosine 2n pi. Let's see what we are going to be getting. So if we are analyzing cosine 2n pi, when n is equal to odd numbers, we have a cosine 2 pi, which is equal to 1. Cosine 3 times of 2 pi, which is also going to be equal to 1. Cosine 5 times of 2 pi, this is also going to be equal to 1. So we know this is going to be this plus 1 over n. So we have a e to the power of 2 pi, evaluating based on the pattern that we are seeing. We have this n over 1 plus n squared. Listing down different terms in order for us to see a pattern may seem very primitive, But we have tried that when we were discussing about our summation, when we were discussing about our APGP. And I was trying to show you it is actually a very, very powerful strategy that a lot of students, they didn't try to make use of. But just by listing down the terms, listing down the different cases, sometimes it extends our ability to think when whatever that we try to write is not going to work. Because we cannot possibly write down everything, but by seeing the pattern that is showing, it gives me an idea of how I can consolidate this into a definite value. I'm going to try the same thing for sine n pi. So if I were to analyze sine n pi, where n are odd numbers, we will be looking at, let's see what is the pattern. Okay, we just need to write down 3. We can probably extend this idea to the rest of the terms. So we are talking about sine pi, which is 0. We are talking about sine 3 pi, which is also 0. We are talking about sine 5 pi, which is also 0. So we are having a minus e to the power of pi. This will be 0. And finally, the last expression here, which is a cosine n pi. Cosine n pi. So here you have a cosine pi. I mean, if you can't work it out like using mental sum, just press it into your calculator. Okay, press cosine n pi into your calculator, you're going to get a -1. Press cosine 3 pi in your calculator, you're going to get a -1. Press this into the calculator and you are also going to be getting a -1. So that helps us to sort of deduce that this is -1 over n. And now we have sort of like evaluated this. And my final answer is going to be equal to n over 1 plus n squared of e to the power of 2 pi over n minus e to the power of minus become plus e to the power of pi over n. N and n can be cancelled, so I have a 1 over 1 plus n squared of e to the power of 2 pi plus e to the power of pi. And now we are at our final question, question number 10, which is actually also a very, very interesting question, especially the last part. Let's see what we are going to be experiencing that we have not experienced before, in the last 9th question. So the question says, use the substitution. Use the substitution, u is equal to 2x plus 3 to find this, to find the integration of x over 2x plus 3 to the power of 3 dx. So we are going to be replacing all the x. And one habit that I think is good when we are doing substitution is to always re-express the equation that we are given for substitution to make the subject the term that we are going to replace. Like for example here, just to be consistent, we didn't need to do this for the last few substitution question because the term that is supposed to be replaced is always the subject already. So in this case, it is not the subject. I'm going to make x the subject. It will be half u minus 3 over 2. This usually will make the whole process of substitution smoother. So I really encourage you to try this so that we can have a consistency, we can have a bit of organization so that I don't need to organize that, try to clear up the mess during the exam itself, because I've already thought of a way to organize the substitution that I'm working on. So we're going to be replacing all the x by this and dx. So I'm going to work out dx du, which is just simply equal to half. So x, I'm going to be replacing it by half u minus 3 over 2. This is just going to be u to the power of 3, and here we have a half du. So the half, I can actually take it out of the integral. Half, I can take it out. Another half, I can also take it out. Combining them together, it is 1 over 4. So I have a u divided by this is 1 over u squared. This divided by this is going to be minus 3 over u to the power of 3 du. It is a simple integration by using just standard results, and in fact it is just like a secondary school's integration. We have this du. It is 1/4 of u to the power of minus 1 divided by minus 1 minus 3 and u to the power of minus 2 divided by minus 2 plus c. So we have here a 1/4 of minus 1 over u plus 3 over 2 u square plus c. And let's not forget to replace u with the expression for x. So my final answer here is equal to 1 over 4 minus 1 over 2x plus 3 plus 3 over 2, 2x plus 3 square, then plus c. And I'm going to combine this together so that I can prove what the question wants me to prove. Or else this is already a good enough solution. Well, these are really good enough answers. So if I were to combine this together, I'm going to skip the algebra. You will be getting this minus 4x plus 3 divided by 8 times of 2x plus 3 square plus c. So comparing this to what I'm supposed to prove, we can see that p is equal to 4, q is equal to this 3, and r is equal to 8. And hence the question says we are supposed to integrate that. And I guess in this case here, we are definitely going to be making use of integration by parts, because it does look too complicated for any of the standard results or any of the fx, f prime x to be applied. But at the same time, because of the first part, we know that integration by parts, splitting up the expression into two parts, can probably be one of the choices if my default strategy fail. And in a way, after we mentally try to process this, we know the default strategy will most likely not work. So let's just try the process of integration by parts directly. Divided by 2x plus 3 cube. So I'm going to be breaking up this into two parts. One is going to be ln of 4x plus 3. The other one is going to be this x over 2x plus 3 cube. So u and dv dx, we know we can integrate this because we just did that in part 1. So I'm going to let dv dx be x over 2x plus 3 cube, where v is the result that I've gotten in the previous part, and that is equal to minus 4x plus 3 divided by 8 times of 2x plus 3 square. U is this ln of 4x plus 3. So du dx here is going to be 4 divided by 4x plus 3. So this is going to be equal to uv, that times this. It is a huge expression that we are looking at here. So it is minus 4x plus 3 ln of 4x plus 3 divided by 8 of 2x plus 3 square. Then v du dx, this multiplied by this. Oh, in fact, this is quite okay, because if I were to take this multiplied by this, 4x plus 3 and 4x plus 3 can be cancelled. 4 and 8, it will be reduced to half. And minus, if I were to take it out, it is going to be plus half. Integration of 1 over 2x plus 3 square. And this is very, very easy to integrate. I just need to move this up so that it can be to the power of minus 2 and integration can happen already. Let me just finish this up. So we have this plus 3 ln of 4x plus 3 divided by 8 of 2x plus 3 square plus half, rewriting this as 2x plus 3 to the power of minus 2. Then this will be this plus 3 ln 4x plus 3 divided by 8 of 2x plus 3 square. This is plus half. This will be 2x plus 3 to the power of minus 1 divided by 2 times of minus 1, then plus c. I'm carrying out the secondary school's version of the integration. So my final answer, okay, not yet. Okay, I'm going to just write one more before I go for my final answer. So it is going to be minus 4x plus 3 ln 4x plus 3, this divided by 8 of 2x plus 3 square. this is going to be equal to minus 1 over 4 of 2x plus 3, then plus c. So this can be the answer. Again, I'm going to just write down one more steps. Most likely it is because SRJC had given the final answer as the combination of these two together. So I'm going to just write that down also. That will be minus, if I were to combine these two together, it will be 4x plus 3 ln 4x plus 3. It is not necessary, okay, for this step. In fact, this is already good enough. Then this plus 2 times of 2x plus 3, this divided by negative, I've already taken out here, divided by 8 times of 2x plus 3 square plus c. And let's end off by going back to what we have started in sine 4x cosine 6x, which we are going to make use of the trigonometric identity again. In 10b, first part require us to integrate sine 4x cosine 6x. Okay, and to integrate this, let's refer again to our formula sheet, because in our formula sheet, we have a list of identities. And looking at this list of identities, we want to try spot an expression that is as similar to this as possible. And to me, that will be this, sine A cosine B. So I'm going to be making use of that identity, replacing A by 4x and B, I'll replace it by 6x. Recoding the first identity there, it is going to be sine replacing A by 4x. So this plus replacing B by 6x. So this is equal to sine 4x cosine 6x plus cosine 4x sine 6x. This will be my equation A. And writing down the other version of the first identity, it will be 4x minus 6x. This is going to be sine 4x cosine 6x minus cosine 4x sine 6x. This is B. And what I'm going to do is I'm going to try to combine them together so that I will be left with a sine 4x cosine 6x, which is this expression over here. And what I'm going to do is I'm going to take equation A plus equation B. On the left hand side, we will have a sine 10x. Then after that, it is going to be plus sine. This is going to be minus 2x. And here we have a 2 times of sine 4x cosine 6x. This will disappear. Now making this the subject, sine 4x cosine 6x is going to be equal to half of this. So 2 divided over half of, we have a sine 10x. Sine minus 2x is same as minus sine 2x. So now we have another way to re-express what we have here into now a half of sine 10x minus sine 2x dx. This is going to be equal to half. Let's factorize it out from the integration notation. And here we will have a minus 1 over 10 cosine 10x. Then minus 1 over 2 cosine 2x. Minus minus become plus, so plus 1 over 2 cosine 2x. Then plus c. This is minus 1 over 20 cosine 10x plus 1 over 4 cosine 2x plus c. And we are going to make use of this result for the last part, which is very interesting. It is something that we have not seen before in the last few questions that we have done, because the question require us to hence or otherwise. We are definitely not going to do it as otherwise. Okay, this is a 1 mark question. Doing it by a hence is the only way for me to achieve a 1 mark solution. Hence, I'm going to evaluate this e to the power of x sine 4 e to the power of x cosine 6 e to the power of x dx. We are supposed to evaluate this as a 1 mark solution. And how are we able to do that? You know what this is testing us? This is testing us on our ability to generalize the idea of fx, f prime x. So let me show you one, and I hope that you can, based on that, to generalize and evaluate this. So one that is closer to what we are experiencing here that I want to show you is maybe this one. 1 over square root of 1 minus x squared. So we know this becomes sine inverse of x plus c. Right? This becomes this. So if we know this standard integral, we can extend this to a fx f prime x scenario. If it is fx f prime x scenario, then it will look something that is like this. Square root of 1 minus x is supposed to be replaced by an fx. Then you are supposed to be able to find f prime x in front. And if you have a scenario that is like this, which is very similar to this, generalizing using this should give me a result of sine inverse of fx plus c. This is what we have been doing for all our fx f prime x, and most likely by now you should be able to do this also. So I'm going to try to apply it here, which means that if I already know something that I can integrate, we can actually generalize this into any other fx f prime x form. Like for example this, if I already know something that can be integrated, then if x is replaced by fx, and if I can find an f prime x in front, then my final answer is going to be when x is just simply going to be replaced by fx. So for this case that is here, fx is the e to the power of x. So x is replaced by e to the power of x, and f prime x can be found in front, which is e to the power of x. Let me just re-express this a little bit better so that hopefully you can see this as something that is similar to this that is happening. So this is my f prime x, and we have a sine 4e to the power of x. This x is replaced, and we have a cosine 6e to the power of x. So this is also replaced, dx. And now, by making use of the same idea, all this x here just need to be replaced by fx, and I will be able to conclude this integral, which is going to be minus 1 over 20. Then we have a cosine 10 e to the power of x plus 1 over 4. Cosine 2x is going to be replaced by e to the power of x plus c. I'm glad we have one question that is like this for us to finish up the entire integration, because this kind of question refine and affirm the way that I'm doing fx f prime x. So now we have finished the whole set, the whole worksheet, all 10 questions together. I hope you are getting a good warm-up to integration already. Like what I was saying, if you feel that you need more integration, please don't stop by, stop here. But although I do feel that, if you haven't gone through the entire video together with me, you probably have already gotten a good enough warm-up to tackle your coming exams. But just in case you need a little bit more of practice, do take out your revision package, practice them. And when it comes to the next exam, just revisit this video again. Go through this with me one more time in a video. It is really okay to redo this set of questions. They are very good questions that I've selected, because by redoing these 10 questions, we actually have gone through most of the styles and most of the kinds of integration techniques questions that you will probably see in the exam. So I've specially curated this set of 10 questions. Do make use of that. Repeatedly come back to this video again. I believe that it's going to give you the best possible kind of warm-up for integration technique. Practice-centric topic which require us to practice and practice and practice.